Hello. So today let's see geometrical isomerism. Geometrical isomerism. In the previous video, we have seen what is isomerism. We have discussed what is structural isomerism. Today we are entering the part of stereoisomerism. Stereochemistry itself is a vast subject, which is a branch of chemistry dealing with different isomers, their properties. So stereoisomerism is of two types: geometrical isomerism and optical isomerism. What is stereoisomerism? Now, in structural isomerism, we have seen that the connectivity between the atoms of a carbon chain is different. I can arrange ABCD like this, BACD, or anything I wish. See, the connectivity is different. Such kind of isomerism we have seen in structural isomerism. Now, in stereoisomerism, the relative arrangement of these atoms in 3D space is differing. Now, I can write it like this. You see, there would be some small difference between these two. There will be some difference in physical properties, but nothing in chemical properties much. So physical properties will be different between these two. So such kind of isomerism is discussed under stereoisomerism. And today our topic is geometrical isomerism. Recapping what is isomerism? Isomerism is the compounds having same molecular formula, but they have different structural formula. So here also the molecular formula would be same. That's why they are called isomers. But their spatial arrangement would be different. So what is geometrical isomerism? Before getting into geometrical isomerism, let's see what is causing geometrical isomerism. The reason why geometrical isomerism is occurring is because of restricted rotation. Now, let me take an example. Let me take C double bond C. You see, now what is the hybridization of carbon here? It is sp2 hybridized, right? So if I write it more precisely, it will be like this. This is a sigma bond, and the pi orbitals are overlapping. They are sideways overlapping. So this is forming a pi bond. We have discussed this thing in chemical bonding under hybridization, Vesper theory. So this is sideways overlap of pi orbitals. Now, when I am going to rotate this molecule by 90 degrees, what would happen? This pi overlap will be broken and the orbitals will be looking like this. There will be no more overlap. So the pi bond is breaking. This is something you don't want to happen. So this kind of breaking, you are trying to avoid it. And the bond energy required to break this pi overlap is just 25 kilojoule per mole, which is comparatively very less. So this is called restricted rotation. Now you don't want to break the pi overlap. So that is why you're going to study atoms in this way. They are having double bond. And because of this restricted rotation, the relative position of all these four valencies of the both carbon atoms, you can see two here and two here. These four valencies are fixed. So relative changes in these positions can lead to formation of new isomers. So such kind of isomers are called geometrical isomers. Now, what is condition for geometrical isomerism? So the condition for geometrical isomerism is number one, they should have restricted rotation. Right? We have just seen the what is restricted rotation. Restricted rotation can be seen in C double bond C, C double bond O, C double bond N, or in N double bond N, and there are a number of compounds. These are the basic restricted rotations we are going to deal mostly under geometrical isomers. So number two, even cyclo alkanes also show restricted rotation. They are also sp2 hybridized, right? Now, sorry, they are sp3 hybridized, but then also they show restricted rotation. Now, the second condition and important condition for showing geometrical isomerism is the restricted site should have different groups. Restricted site should have different groups. What do I mean by that? Now, there is C double bond C like this. Now, if I keep a methyl group here and a methyl group here, there is no point of discussing geometrical isomerism here because I cannot interchange with one atom to the other. So I have to interchange within the carbon atom. So changing the same CH3 molecule doesn't make sense, right? So in order to show geometrical isomerism at the same carbon or the at the same restricted center or the restricted site, same groups should not be there. It can be like this. I can have CH3 here, I can have H here, and I can have CH3 here, no problem. But I can't have the same groups on the same carbon. That is the thing. So these two are important conditions for showing geometrical isomerism. Now, the first geometrical type of geometrical isomerism we are going to see is cis-trans. Now, when people started to like explain about geometrical isomerism, they needed nomenclature to explain different types of molecules. Let's see the need of nomenclature aside. First, let's see what is cis-trans isomerism. Now, when there are similar groups on both the atoms in a restricted site. So if I have A here, B here, and I have a here and a C here, in such kind of scenario where I have the same group on both the carbons, in such case we use cis trans type of nomenclature. So what is cis? What is trans? Cis compounds are like the compounds which have the groups on the same side. Trans are on the different side. Now, see here. Here A and A both are on the same side. Like I meant above carbons. See, so such kind is called cis. This is called a cis isomer. Now, there can be a scenario where I can place A down, or I can put this A up and I can bring this A down. So such kind where they are on the opposite sides. If we are taking this convention, this is up and this is down. If they are on the opposite sides, according to our conversion, I mean according to our convention, so such kind of compounds are called trans compounds. So this is called cis compound. This is called trans compound. So let's see some examples for cis and trans. Very basic example: C double bond C, CH3, CH3, and let's keep H and H here. What is this? It is cis. This is number one cis compound, and this is a butene. Cis butene. Sorry. Cis butene. What would be the trans compound for this? It will be like this: CH3 and then CH3 here. So this is trans butene. Okay, this is some of the example. One of the famous example and a very important example, majorly asked, the cis-trans relationship between malic acid and fumaric acid. Now, let me take this, right? C double bond C, COH, H, H, COH. What is this compound? It is a cis compound, right? And what is this compound? COH, COH, H and H. This is trans. This is cis and this is trans. Now you can clearly see here, here the two groups are on the same side according to our convention. So it is a cis compound. Here they are on the opposite sides. It became trans compound. Now this compound is called malic acid. And this compound here is called fumaric acid. quite important names. So trans compound of dicarboxylic acid is called fumaric acid, and cis is called malic acid. They both have different physical properties, so that's why these become a very important example in cis trans nomenclature. So this is cis trans. You have to check cis trans whenever you have similar groups on both the atoms. Now let's see syn and anti. So syn and anti nomenclature is used in three different cases. If the compound is aldoxine, or if the compound is ketoxine, or you can see in azo compounds. So you can also use syn anti in phenyltrazone compounds and hydrazone compounds. So, but basically these three are very important uh, categories under syn anti. What is syn anti? In syn anti, you compare OH and H, their relative positions. You compare relative positions of OH and H. Now, let's see what is aldoxan. So, let's see the case of aldoxan, right? What are aldoxan? Aldoxines are formed when aldehyde, so aldehyde, when it reacts with hydroxyl amine or NH2OH, simply it's called hydroxyl amine, it is forming aldoxan. So aldoxan looks like this. Aldehyde is R, C, H, double bond O, right? So aldoxan looks like this. C, double bond C, right? You have OH, you have R here, you have H here, and then, sorry. There's an O here, and then you have the lone pair. 1, 2, 3, 4, 5, 6, 7. Yeah, this is a lone pair. Now you have to compare OH and H. So in case of aldoxams, you can see OH and H here, they are on the opposite sides. If they are on the opposite sides, when OH and H are on the opposite sides, then you name them anti. Okay? Opposite side, it's anti. And when OH and H are on the same side, then you call them syn. Okay, syn anti. You can compare it with cis trans to remember it. Cis means same side, so syn also means same side. Trans means the opposite side, so anti means also opposite side. You can see in aldoxams, you can see H and OH are on the different side. So this is an anti-aldoxan. So if I want to write a syn compound for this, I can write like this. So this will be syn. Now, in case of ketoxames, ketoxame is also formed by reaction with hydroxylamine. So when ketone reacts, what is ketone? You have one alkyl group, you have another alkyl group, you have double bond. This is called ketone group. When it reacts with hydroxylamine or NH2OH, ketoxame is formed. Ketoxame looks like this: R1, C, R2, double bond O, H, and then a lone pair. When it comes to comparing ketoxames, it is out of syllabus, but then also, when you are comparing ketoxames, you have to check for alphabetical priority. What is alphabetical priority? What do I mean by this statement, alphabetical priority? Now, we can clearly see that there are two alkyl groups here, right? So, if this is a methyl group and this is a ethyl group, E has less, like it comes first in the dictionary, right? So, this will have the first priority. So similarly, if I have a ethyl group and I have a propyl group, what will be my priority? It goes to ethyl group. Okay, because E comes first in a dictionary. If I have a methyl group and a propyl group, methyl goes first. So ethyl has the first priority. Okay, and then we have double bond here. The first priority group and the double bond are on the same side, so this will be a syn. And if they are on the opposite side, then it becomes anti. This is about ketoxines, the syn and anti in ketoxine. In azo compounds, azo compounds are where you have N double bond N. So when you have N double bond N, check for the lone pairs. So if lone pairs are on the same side, then it will be syn. And if lone pairs are on the opposite side, R and R1, then this will be anti. Okay, this is about syn and anti. We can clearly see that in aldoxymes, we have to compare OH and H. In ketoxymes, you have to give alphabetical priority. And in azo compounds, you have to check for lone pairs. Okay, syn means on the same side, anti means on the opposite side. Now, let's see ZE nomenclature. This is a pretty, very important nomenclature of geometrical isomerism. Now, what is ZE? You can find in books that it is given EZ, but ZE would be a better convention. I'll explain you in a while. You call it EZ nomenclature, so you can remember it like ZE. Now, we have seen cases of geometrical isomerism where you have the same groups like this. Sorry, CH3, and then you have H. Now, you can clearly see you have same groups here, so you could compare. And we have seen in case of aldoxymes and ketoxymes when we have H and OH. Now, what if I give you an example like this? When I have here fluorine, I have chlorine, I have bromine here, and then I have iodine. What do you do now? This is showing geometrical isomerism, right? It has restricted rotation and all the groups are different. It is showing geometrical isomerism. But under what nomenclature should I keep this compound now? So that's why we have introduced a new nomenclature that is called ZE nomenclature or EZ nomenclature. Here in ZE nomenclature, very important, you give priority. You give priority to groups. How do you give priority? So scientists are thinking about how to give priority, and there are three scientists, CIP. So his name was Khan, his name was Ingold, and his name was Prelog. These three scientists came up and gave SIP rules or CIP rules or whatever you want to call it. SIP rules. So here in SIP rules, it mentions how to give priority to different groups. They gave it for RS configurations, but that was extended to EZ. Now, here, listen here. So you have four different groups: fluorine, chlorine, bromine, iodine. Now, how do I give priority? The SIP rules say that I'm going to shorten this, condense this SIP rule so well that you can remember that number one, you have to check for molecular weight. Okay, molecular weight. And number two and number three we'll discuss later. Now let's see molecular weight. Now here, when a molecule or see, when the group attached to the carbon has more molecular weight, it automatically gets more priority. Now, fluorine, chlorine, bromine, iodine. So we have to check for each carbon separately. Let's check for, I name this carbon 1 and I'll name this carbon 2. For carbon 1, out of fluorine and chlorine, which has more molecular weight? Chlorine has more molecular weight, right? So chlorine gets the first priority. Now, for the second carbon, bromine and iodine. Among bromine and iodine, iodine has more priority. Give it number one. And fluorine gets this second priority here, and bromine gets the second priority. Now, the higher priority groups are on the same group. Very important. When high priority groups are on the same side, then you give them the name Z. Same side means Z. So Z and Ne come from the German names Zusammen and Entgegen. Uh, Pardon me for my German pronunciation, but Zusammen means same side and Entgegen means opposite side. So higher priority groups on the same side are given Z. So this, they have the same side. So you can give it name Z. Okay. And then when you want to give like this, how can I write an E compound for this? Write iodine here. So here, the higher priority groups are on the opposite side. When they are on the opposite side, you give them E. So that's why ZE convention would be better. Because cis trans means same and opposite. Sin anti, same and opposite. So Z means same, E means opposite. So that's how you can remember it with ease. So you can see here, Z is on the same side, E is on the opposite side. What are the two other SIP rules? So we have seen molecular weight. Now, you have to, number one, check for connecting atoms. What does this second rule mean? Check for connecting atoms. Now, if I have like this, I have carbon here, I have hydrogen here, I have carbon, hydrogen here, and a carbon here. Now, this carbon is connected to oxygen, okay? Let's say OH group. And this carbon is just hydrogen. Now, how do you compare here? All, yeah, you got them. Let me replace this hydrogen with something else. What do I replace it with? Deuterium. Okay. I keep deuterium. Now here you have to check. The first connecting is carbon. The first connecting atom is carbon. Now here the carbon is again connected to oxygen. The carbon is again connected to hydrogen. Here you can't go with molecular weights. Okay. So you have to check for connectivity. Now here carbon is connected with oxygen. Oxygen has more molecular weight. So you have to always check molecular weight of atoms. Connected. Atoms connected. So here oxygen. Oxygen has more priority. So this will get the first priority. Right. And then of course, if CH3 is like this, I have to take CH3 here. So carbon is connected with hydrogen. This will get the second priority. Here carbon is connected to hydrogen, but here it's just hydrogen. It will get the first priority. So you have to check for connectivity. If I have carbon, oxygen, carbon, fluorine, carbon, bromine, what do you choose? I'll choose carbon assigning priority. You'll go for bromine first, and then fluorine, and then oxygen. Okay, so that's how you have to check for connectivity. Next one, the third rule for which they got Nobel Prize, and I never understand why did they get a Nobel Prize for this. It's the phantom atoms. Okay, phantom atoms. What are phantom atoms? Now, so under phantom atoms, what does this rule say is consider multiple bonds as single bonds. So let's see two ways of visualizing it. Let's see a normal view. Let's see the bookish view. Now, if C triple bond C, if C is connected to a triple bond C, how do you see for checking priority? So you write like this: carbon, carbon, carbon. So, and you can see this carbon is also connected with this carbon. So you will write another three carbons attached to this. Okay. So these are called phantom atoms. Okay. These are called phantom atom or ghost atoms. So you have to consider multiple bonds and single bonds. And this is how you check for connectivity. So in books, it is also written like this. C triple bond C is like this. C, 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 C. Now, this carbon is connected with three different carbons. And this carbon is connected with three different carbons in each perspective. So that's these are phantom atoms, and this is how you have to check for connectivity. Okay, this is how you check for connectivity. So let's see some examples of EZ nomenclature, right? So uh, let me see some examples, right? Right. Now, C double bond C, CH2, CH3. You have hydrogen here. And you have CH3 here. And then you have hydrogen here. Now, yeah, I'll take a CH3. You can assign priority here. All three are different. No, sorry. So just add another one, right? So look at this example. Now, wait, I'm sorry. So let's take C2H5. That perfect. Now let's check for carbon 1 and carbon 2. For carbon 1, more priority will go to methyl group because carbon. Now here, you see, this carbon is connected with this carbon, and if I write this more simply, it's like this: CH3, sorry, CH2, CH3. Here carbon is connected with carbon. Here also carbon is connected with carbon. So here this carbon is connected with only hydrogens. Here this carbon is connected with another carbon. So carbon is connected with carbon, carbon connected with hydrogen. Cc and Ch. Whom you will give more priority? Of course this. So this will get the first priority, this will get the second priority. Same priority groups are on the same side. So this will be Z. So this is summon, which means the same side. And if it is like this, C3H, right, 7, and then C2H5, and then CH3, and then hydrogen. So more priority is here, more priority here. This would be E. So this is called ZE. And we can see, just recapping ZE nomenclature. So ZE nomenclature comes in place when all the four groups attached are different, and then you give the ZE nomenclature based on priority, and priority is decided by CIP rules, right? And CIP rules, what are CIP rules? First, you check for molecular weight, check for directly connecting atoms, and then treat multiple bonds as single bonds. Those are called phantom atoms. So you can write them in two ways. You can represent like this for a simpler way, and if you want to go for the bookish way is here. And then we have seen some examples. So that is ZE. We have seen complete geometrical isomerism, and a last topic is left, that is stability orders, right? So among cis and trans, when we are discussing about molecular formula, when we are discussing about molecular formula, sorry, melting point. Sorry, I'm really sorry. So melting point. Melting point of trans is more than cis. Why is melting point of trans is more than cis? So trans is something like this, right? So you have A, you have A here. Better packaging of atoms is seen place. So that's why melting point would be higher. So reason is packing of atoms. So boiling point, when you're discussing about boiling point, cis has more boiling point than that of trans. Why? In cis, there is dipole moment. So there is some dipole moment mu. So because of dipole moment, dipole attractions are seen. So there will be some attraction between compounds, and then because of attractive forces, boiling point will be more. So cis, the boiling point is more, and then cis is more soluble than trans, because cis is a polar compound because of the uh, dipole moment seen here. So cis is soluble in polar solvents, and trans has less solubility. So these are stability orders, and oh, we came to end. So the last topic is formulae for number of geometrical isomers, which are according to me and according to my chemistry teacher, my chemistry sir, these are not useful, but then also you can remember them. So when the compound given is symmetrical, then the number of geometrical isomers is 2 power n. And when the compound is unsymmetrical, you have two cases. When you have odd number of carbons, when you have even number of carbons, when you have odd number of carbons, you can write it as 2 power n minus 1 less 2 power n by 2 minus 1. And when there are even number of carbons, you can write 2 power n minus 1 plus 2 power n minus 1 by 2. Okay, where n is, the number of carbon atoms and stuff. So these are formulae for geometrical isomers. And then we have seen ZE, we have seen syn anti, and we have seen system. We have seen restricted version. And that's it for today. Thank you.